Thank you for your interest in our work on latent belief space motion planning under cost, dynamics, and intent uncertainty. I am Dicong, and this is a joint work with Yibiao Zhao and Chris Baker at ICAI. We are a startup in Cambridge, Massachusetts, building autonomous trucks. Uncertainty is pervasive in autonomous driving and robotics, both about physical states such as position, velocity, and heading, and about latent states of the world, such as whether another driver intends to cut in, merge ahead of our vehicle, or behind us. Partially observable Markov decision processes can model this uncertainty, but they are intractable to solve in general. In this work, we present a method for trajectory optimization in POMDPs with non-Gaussian uncertainty over discrete latent variables. We show that this setting captures three important classes of challenges in autonomous driving, namely scenarios with uncertainty about the reward or cost functions, scenarios with uncertainty about the dynamics, and scenarios with uncertainty about the latent intentions of other vehicles. As a one example, consider a lane change scenario, in which our vehicle must change to the adjacent lane, but there is another vehicle adjacent to us in that lane. On top of the uncertainty about the continuous state of that vehicle, the latent mental state of the driver on that vehicle is also uncertain. The driver may be aggressive, and hence will refuse to yield to us. On the flip side, the driver may be nice, and cooperates with us by yielding. So, how do you solve this problem? Analogous to policy tree representations in discrete POMDP settings, we build a trajectory tree starting from the initial belief, and create branches by assuming the maximum likelihood outcome and observation for each possible latent state value through the planning horizon. Each leaf node of the tree represents one contingency. Here, there are 4 paths through the trajectory tree representing 4 contingencies. For example, the leftmost path consists of 2 observations that the other driver is aggressive, and the planned trajectory changes lane behind the vehicle. The rightmost path consists of 2 observations that the other driver is nice, and the planned trajectory merges ahead of that vehicle. The partially observable differentiable dynamic programming, or PODDP algorithm we derived, applies over the entire trajectory tree to optimize all contingency plans simultaneously by backpropagating the gradient of the value function to generate an optimal plan under multimodal uncertainty. Previous work in this space has considered trajectory optimization in belief space, but they are limited to Gaussian uncertainty and do not handle uncertainty over discrete latent variables as we do here. General-purpose POMDP solvers can handle discrete and continuous state variables, but the extension to continuous actions is challenging, which trajectory optimization methods can handle naturally. Belief space planning has been applied to the active SLAM problem, and much of the research on intention-aware motion planning is relevant to our work. In the experiment, we set up 3 scenarios to demonstrate our method's capability to handle 3 important sources of uncertainty. The lane change scenario shown previously demonstrates the capability to handle interactive intent uncertainty. For uncertainty about goals or hazards, we set up a scenario called T-maze, where we place an agent in a corridor with a T-split at the end. The agent is searching for a goal, which is difficult to observe near the entrance of the corridor. The goal can be either on the left side or the right side. For uncertainty about dynamics, we set up a scenario with an agent moving towards a goal on a multipath, but there may be a smoother path to the right. The agent needs to explore in order to find an optimal trajectory towards the goal. In an experiment, we compare PODDP against 2 different baselines, namely, the maximum likelihood DDP, which always assumes the latent state with the highest belief to be the ground truth, and the probability-weighted DDP, which weight the cost for different latent states by their beliefs. Qualitatively, PODDP produces ideal solutions within our experimental scenarios, which are robust to uncertainty, and optimize the trade-off between the cost of exploratory actions and the potential benefit of the information gained. And in comparison, the baselines often generate poor solutions, which are sensitive to noisy observations and do not explore. Quantitatively, our experimental results showed that our proposed method, PODDP, outperformed all the baselines significantly in terms of cost in all the scenarios. For more details of this work, please refer to our paper and website. Thanks for watching.